All right, thanks for the intro. So, hey everybody, my name is Milecia, and I'm a developer advocate at Iterative AI, where I mainly focus on our open source tool, DVC. So if you do have any questions during the talk or after the talk, feel free to reach out to me directly on Twitter at Flipped Coding, or you can reach out to the whole team on Twitter at DVC.org. But today, I want to talk to you about just a problem that machine learning engineers run into every day. And we'll talk about using reproducible experiments to make better models and what that really means. So let's just jump straight into it. There's some common issues that come up with every machine learning project, no matter how well defined it is, how much data you have, all that good stuff. Usually you're trying to find the best combination of hyperparameters, your algorithm, and your data set so that you get this really good model that you can finally push to production. But over the course of even just a week, you make hundreds of experiments. So you're going through, you're changing algorithms to see which one performs better. You're updating hyperparameters to figure out which combination gives you the better results. You're maybe even changing data sets because business requirements have changed, or you just have more information. But right now you have to keep track of all of those changes yourself. So I've seen teams that keep track of their metrics and the associated hyperparameters in spreadsheets. I've seen teams try to associate a zip file with every Git commit that they make. And it just gets really messy because over time, it's hard to follow all of those changes. So maybe you have some really elaborate spreadsheet system for tracking your experiments, but somebody else on your team actually just makes a bunch of different zip files to try to keep all of the code, the configs and the data just bundled together. So over time, as you're doing all of these different experiments, keeping track of every little change you make gets super tedious because you get to this point where you're like, oh my gosh, I remember there was that one experiment and it gave me this ridiculous accuracy of like 97%. What did I do to get that model? What hyperparameters did I use? Was I using this algorithm when I did that, or was I using a different one? Was that the data set that they sent a month ago, or was that the data set from last week? So you see how over time it gets hard to keep track of all of those other experiments you run. And that's why we're going to talk about fixing that problem today, because nobody wants to have to keep track of all of these really tiny changes that they make, maybe every few minutes. So we definitely need to fix that problem. And the way that we do that is by using tools that help us bundle everything together. So when you have the code and data associated with each of your experiments, it's really easy to go back to any experiment you run. So you're able to basically bundle together your data, your configs, and your model, and you do that for every experiment you do. So this sounds like maybe kind of magic or fancy or something, but there's plenty of tools that handle this for you. But of course, today we're talking about hyperparameter tuning. So now that you know our issue is with keeping track of all of these tiny changes, the metrics that are associated with them, the code, the data, the configs, let's go through a real example of what this is kind of like in practice. So we're going to start with just some basic hyperparameter tuning. And I'm sure a lot of you know what hyperparameter tuning is already, but just in case you don't, hyperparameters are the values that define your model. So for example, if you're using something like a neural net, maybe you need to specify the number of layers that you have in that net. Or maybe you're working with a random forest classifier and you need to specify the max depth for that. So these are the parameters that define those parts of your model. Maybe you have some kind of learning rate that you need to play around with, or you have a momentum that you want to try different values for. So these are the hyperparameters that I'm talking about. And a couple of common methods used for hyperparameter tuning are grid search and random search. So with your grid search, let's say you have three hyperparameter values. You have your learning rate, your momentum, and I don't know, maybe the number of layers in your network. So you have these three hyperparameters, right? And each of these hyperparameters has 10 values each. So with a grid search, you're going to go through every possible combination of those parameters. And if you think about it, you have three hyperparameters, 10 values each. That's a lot of different experiments. And I'm not sure about you, but I don't want to have to keep track of every little change that I'm making when I'm going through a grid search, because that makes it take even longer. Like we're already going through all these values, and now I have to stop every time and be like, oh, well, this was the loss associated with this experiment when my learning rate was 0.5 instead of 0.1. So just imagine doing that for every little thing, every grid search combination. That is what we're going to try to not worry about. And then random search is very similar to grid search in just the way that it operates. So you still have, let's take our example of our three hyperparameter values. And instead of taking 10 discrete values, or you could keep those 10 discrete values, what random search will do is just, well, randomly hop around different combinations of hyperparameter values, and that's it. It doesn't exhaustively go through every possible combination. It just jumps around. And usually if you are doing a random search for a similar amount of time that you would a grid search, you'll come out with more optimum values. And it's just because the random search gives you a broader range of combinations a lot faster than grid search does. But now that we've, talked about our problem, we're doing this hyperparameter tuning with grid search and random search, and we have all of these little incremental experiments we need to run, and we don't really want to have to write down everything as we go, right? That's where a tool like DVC comes in. So when you're thinking about DVC, remember it's open source, so you can come look at the code, tweak it however you want. It works on top of Git. So it's not something that's like its own standalone application or service. It's just a little command line tool that you add to your project, and it tracks your code and your data together by taking advantage of Git. And it's not opinionated at all. So there aren't any libraries you have to add to your code. You don't have to call any APIs. You don't even have to use any particular programming language. You can use Python, JavaScript, which, yes, people do use JavaScript for machine learning, and I am definitely people. You can use it with R, Julia, whatever programming language your project is in. DVC doesn't care. It's just the CLI tool that helps you manage your experiments. It helps you do data versioning. So when you do have those updated requirements from the business and you need to expand your model, but you already have these existing data sets and you don't want to worry about, well, which data set am I working with? DVC tracks and versions all of that for you. And kind of the way that it works is that it has metadata it associates with each experiment that it pushes to a custom Git ref. So that's how it's tracking all of these experiments in the background for you. It's just adding things to the DVC cache. When you decide an experiment is good enough, you commit it, and then it's yours forever. You can share it with people on your team. You can go back and redo other experiments. Like if you run 100 experiments and you see number 71 has the best loss value or something, you can go back to that experiment and reproduce the exact conditions that you ran it in. So that's a few reasons why DVC is such a cool thing. But what it does, whenever you're ready to run an experiment, you'll execute this DVC exp run command. And what happens is it executes whatever training script you have. If there are other stages in your pipeline, like maybe you train your model and then you have some kind of evaluation step where you print out your metrics to some kind of JSON file or maybe a CSV, whatever it is you use to store your metrics. But what happens is you run your experiment, DVC takes whatever the current code is, whatever the current data version is, and whatever your configs are, and it just neatly packages them together and associates all of that with this model that you get at the end. So when you run an experiment, you don't have to pay attention as closely anymore. You don't have to worry about, well, what data set am I using? Did I change this code this time or did I change that code last time? Was this the algorithm I was working with? Now you don't have to ask yourself those questions and lose sleep at night over missing out on that really good model that you had. You're able to run your experiment. DVC bundles everything together so that whenever you're ready to come back and maybe compare different experiments or make changes to things and try again, you already have this neat little packet. So you're going through this hyperparameter tuning and you have all of these different experiments. So each of those experiments with DVC looks just like this. You have your data, your params, your model, and the code that makes up the model. So you have everything that you need to go back to any previous experiment and pick up training from there. Maybe you see that right now you don't have a best model, but you have a general direction of where to go. So instead of having to go through your spreadsheet or, bug people about going through zip files and figuring out what metrics are associated with what, now you have just one tool where you can look at everything and then you can start pulling out those different patterns for where you need to go with your model next. So let's say you've run an experiment with DVC, just one experiment like you see here. So this is an example of the table you'll get after you run an experiment. And you see, you can take a look at your metrics. You can take a look at the hyperparameter values you were using. So in our case, our hyperparams are this train.nest and this min split value. And this is just one experiment. So it doesn't look like it's doing a lot right now. But we're gonna go through this hyperparameter tuning. And what that means is that you already have some set of values, right? You already know your hyperparameters. So what we're gonna do is use DVC to set up a queue of experiments. So basically it's like writing a little script to do a for loop, and you make all of the combinations that you want to use for your hyperparameter tuning. So we set up a queue with these different hyperparameter values, and we get a table that looks something like this. So what's happening here is that we've queued up a bunch of experiments with a grid search. So we have two hyperparameter values, and each one has, I think, maybe 5 each, just to keep things simple. But this is just a small snippet of what this whole metrics table looks like. So for example, if you are doing some kind of training experiments and you're on a team, because of course you're probably on a team, you might want to look at the experiments you have in your queue just to make sure that you're not repeating something that's already done. That's the cool thing about DVC is you're able to share these experiments. Since they're all neatly bundled up, it means anybody on your team can take your experiment and resume training from that particular set of code, hyperparams, and data. So when you have a bunch of people running a grid search or a random search, there's bound to be some overlap in those values, right? So maybe you use this table to look through and be like, oh, well, they've already run experiments with this combination of hyperparams. I'm just gonna remove those from the queue and run these new ones. That's the kind of flexibility that you get when you're using something like DVC. So we've looked at our queued experiments. We've decided that, this combination of hyperparameters, it's fine. So we'll run all of the experiments now. And the cool thing with DVC is that you have all of these experiments in your queue. Maybe you have hundreds just in your queue. You can run them all at the same time in series, or you can run them in parallel. So if you're offloading things to the cloud, maybe running experiments in parallel will give you, I don't know, maybe it'll save you some time on your overall research. And it can also save you some resources. If you have 2 or 3 machine learning engineers running hundreds of experiments in parallel, you're doing a lot of work really fast. But let's say you've gotten all of the experiments in your queue, they've run, and now you're ready to look at the results from those. You can just go back to your terminal, run that DVC exp show command, and you'll see all of the experiments that were run from your queue. So you can look at your average precision, which set of hyperparameter values are associated with that. And you see we have kind of a decent range of average precisions here, which is probably what we would expect given how widely our hyperparameter values swing. But it looks like if we have a larger NEST and a larger min split, that we get a better average precision. So even though maybe this experiment or this set of experiments didn't give you your, golden model, you at least know which direction to go. So you might want to compare these different metrics just with a plot, because sometimes a picture is just easier to understand than the table. So we would use this plots diff command to compare 2 or more experiments. So maybe you just want to get a quick visual, or you want to check with your other machine learning or data science friends and see if your results actually make sense. So you'll run that command. We just have these two experiments because they were the furthest apart. But if we look at these plots, this is definitely something you would show to, a colleague, another data scientist, ML engineer, just so maybe a sanity check, because you might be looking at this table of experiments and you're like, well, I think these two might set like some bounds for what our hyperparameter values should be going forward. And then you pass this plot or these plots on to somebody else to review, and you see what they think about it. And then y'all decide on which experiment to go from here. Maybe you pull another one from the table to compare, but you have this flexibility to just jump around different experiments and quickly compare them. So can you imagine trying to make a plot with just these two experiments from that giant table of experiments if you didn't have some kind of like tracking slash versioning system? It takes a while. You might need to make some separate tool just to do that. So we don't want to do extra work, because why? It's hard enough to train the model, let alone make a whole system to keep track of everything for you. But this is just one of the ways you can take those metrics and visualize them. So let's say, you've talked to your friends and they're like, maybe you should run some more experiments. So we go back, we set up a queue with some more values for our hyperparameters, and we run this, and we're trying a random search this time, just because we're like, well, it looks like larger values are better, but maybe we didn't try a good enough range of smaller values, because we jumped from like 26 to 100 and something pretty quick. But we're still pretty sure that our NEST and min split should be larger, but we just really want to make sure before we rule out those small values. So we have 3 new experiments in our queue. We check with everyone to make sure nobody's tried this set of values, and we decide to run them. So again, we just open up the terminal, wherever your terminal is. It could be in your IDE, it could be just a plain old terminal, it could be something in your cloud, wherever it is. You can open that up and run all of your experiments. And then again, we'll run this exp show command to look at our table. And would you look at that? It does look like the larger values are probably going to be better in general, right? Maybe not as large as, 3,400, 9,400, but definitely above 92, maybe above 100. We're just trying to figure out what is the right approach. So you keep running these experiments and you keep setting up these queues. So again, you set up another queue of experiments because those didn't give you the results you were looking for. And now you're running through more experiments from a random search, and you've isolated the NEST values. So we're trying to figure out which hyperparameter maybe has a larger impact on our model's performance. So we're going to keep the NEST values under 100, and we're going to keep the min split values over 350. So we've come up with this idea that we just want to test out. So we'll run some experiments again, and we'll look at our table again. So if we look at this, maybe we should definitely factor in the NEST, because it looks like having that as a lower value is doing something. We don't know. But again, we're like, well, colleagues, friends, what do you think when you see these results? And you might not need them to see your entire table of experiments, mainly because that'll be a lot for them to parse through, but there's probably a few that you just have, you're like, well, I'm not sure which one to choose. I'm not sure what these results mean. Which way should I go? So we grab a couple more experiments, one from the newer ones, one from the older ones, and we look at the difference between those metrics. So again, we have this plot that we're thinking about sharing with all of our colleagues so that we can get some feedback. Maybe they'll see something in this experiment data that they're like, oh my gosh, I remember I was looking at this problem and my results were way off. Maybe we should just start with your experiment. And now everybody's pulling down your code, that data set associated with it, and your configs. So everybody can jump in on this great new direction that your experiments is taking them. So you run all of these different experiments and you end up with a table that looks even bigger than this. And this has quite a few different experiments on it. So you have this giant table, but this is probably a lot better than worrying about having a spreadsheet that has links to zip files that might also have a link to some Git commit, and then things get jumbled. If somebody edits the spreadsheet in the wrong way and the rows get shifted, it's so much easier to just have a tool that's tracking everything for you. It's making sure that if you did want to go back to any of these previous experiments, you could. So now that you see how DVC works, you have a tool that does all of your code and data tracking for you. It adds reproducibility to your project because you have these little bundles that take you back to any experiment you run. And you can share all of these things with anybody on your team. So there's no more, well, I did this experiment on my computer. I don't know why you're getting different results on your computer. Now you have a way to keep everything, what's the word? Consistent. So with DVC, you have a tool that keeps all of your experiments consistent, regardless of what environment you're running in, which means when it's time to go to prod, you know exactly what it's going to take to get the exact results you've already been seeing. So now that you've seen what it's like to solve the nightmare of keeping track of all of these different experiments, let's wrap up with a few key takeaways. The first thing, I hope that you see adding reproducibility to your experiments is important. So when you are doing a grid search and you have these hundreds of experiments and you do find maybe a handful that you want to test a little more, now you have the ability to do that. Regardless of when you ran that experiment, that little bundle with your code, hyperparams, and data will always be there. And then DVC is a great tool that helps you track every part of your experiment. I think it's the only one that bundles your code and your data together. But I do say, don't be afraid to try new tools. So DVC is open source. It's just a command line tool, and you don't have to add anything to your code. But there are other tools out there like MLflow or TensorBoard that might fit your needs better. So just try out different stuff to see what fits you the best. But if you do have any questions, I'll be around in the spatial chat, and you can still reach out to me on Twitter at Flipped Coding. But really, if you have any deep questions about DVC or how it compares to tools like MLflow or TensorBoard, you should definitely join our Discord. So the link is down here in the corner, but this is where we talk about all things ML ops. So thank you for your time, and I hope that you were able to learn something from this talk.